Yeah, it's really my great honor to have this opportunity to share our experience and thoughts on how infrastructure software ecosystem can benefit from the emerging solid-state drive with built-in transparent compression. We know that as the CMOS technology scaling is reaching to its limit, the computing infrastructure is transitioning from the traditional CPU-only homogeneous computing towards more domain-specific heterogeneous computing, where the certain computation tasks migrate from CPU to other computing engines, including the standalone PCIe accelerators, the smart network card that offloads network processing from CPU, and the emerging computational storage drives that offload tasks such as compression and encryption from CPU. So altogether, they complement with CPU to form a truly heterogeneous computing infrastructure. So in the heterogeneous computing landscape, regarding the commercialization of computational storage, data path transparent compression apparently is the first low-hanging fruit for us to pick. Its basic idea is very simple. Compression is done in hardware on the I/O path, completely transparent to the OS and the user applications. Our current product uses a single FPGA to handle both a flash control and a per 4K byte zlib compression. And we implement flash translation layer in a kernel space driver that exposes the storage drive as a standard block device to the Linux block layer. So then the Linux can treat our drive as just as a standard block device. So this cartoon further illustrates its difference from the current practice. On the left-hand side is a current practice where we use either CPU or accelerator to handle compression and deploy normal SSD. The right-hand side shows the computational storage drive with data path transparent compression. Here, a single FPGA combines the functionality of flash memory controller with the hardware compression engine. We handle all the FPGA design and the programming to enable a very convenient plug and play turnkey solution for end users. So by combining the SSD and the compression functions together into a single chip, the storage drive frees up the host CPU cycles and minimize the data movement and enables the compression throughput to scale with the total storage capacity. So this slide shows the basic FIO testing on our drive and also on a competing high-end NVMe drive. So both are 3.2 terabyte. And the FIO generates heavy I/O workload across the entire 3.2 terabyte storage space. The two figures here show the random IOPS when each I/O request is either 4 kilobyte or 16 kilobyte. So in each figure, the horizontal axis is the read percentage in the I/O workload. As the workload changes from the read-only to write-only, the IOPS of the normal NVMe drive significantly drops simply because of their internal garbage collection overhead. In comparison, in our drive with built-in transparent compression, we can on the fly reduce the write data traffic, leading to a much less internal garbage collection activity. So as a result, not really surprisingly, our the storage hardware with built-in transparent compression can achieve much higher IOPS as shown in the figures here. So this table further elaborate and on the comparison among different options of implementing data compression from many different aspects, such as CPU overhead, the scalability, impact on latency, and the easiness of the integration. Clearly, in storage, transparent data compression is the most desirable option. And then naturally, one may ask if such a product is so good, why we're not seeing such drives on the market today? The simple answer actually is it's too hard. It's very hard to design and implement such a product. So the true challenge goes far beyond implementing the data compression and the decompression hardware engine. So as illustrated here, for normal solid-state drive without built-in data path transparent compression, each 4 kilobyte LBA simply maps to a 4 kilobyte flash memory physical block address, or PBA. Such a regular and uniform LBA and PBA mapping make it very easy, or really relatively easy, to implement the flash translation layer that can support high speed and sufficient storage stability. But in comparison, in the case of a storage drive with built-in data path transparent compression, the compression ratio could largely vary from one 4K byte to the other 4K byte. So given such a random data compression ratio variation, the storage drive must appropriately handle the mapping between each 4 kilobyte LBA and its variable length data block location in the physical flash memory. So this makes the data mapping inherently irregular and very random, which fundamentally make it much harder to implement the flash translation layer that can support high speed and the sufficient storage stability. So if you know the challenge of implementing normal SSD without built-in data path transparent compression, you will much better understand the true challenge of implementing such a storage drive with built-in transparent compression. And that is a major reason why we still do not see such a product widely deployed on the commercial market today. And at ScaleFlux, after 2 years of development, we have very recently launched such a product for the first time on the market. And we have seen significant interest from all kinds of customers and users. So operating as a standard block device under Linux, our storage drive can be seamlessly deployed in today's infrastructure without changing any single line of code. Since many our customers are database users, here we just show how the most popular open source database, MySQL, can transparently benefit from the storage drive with built-in transparent compression. The figure here on the left compares the TPS of the Sysbench read-write workload with 2.4 terabyte raw data set. Compared with the normal NVMe drive, the drive with built-in transparent compression can reduce the data footprint from the 2.4 terabyte raw data set to 0.9 terabyte, and meanwhile improve the TPS by about 50%. The figure on the right compares the effective cost per user data gigabyte. Users can just conveniently enjoy all the benefits and without any change to their existing software infrastructure. So if we move forward beyond such a simple plug and play usage model, the transparent compression could open a door to very exciting new innovation opportunities. When using normal storage drive without transparent compression, the utilization efficiency of the logical storage LBA space is always equal to the utilization efficiency of the physical flash memory inside the drive. But transparent compression, for the first time, decouples the logical storage space utilization efficiency from the physical storage space utilization efficiency. In particular, as illustrated here, with built-in transparent compression in the storage, we no longer have to fill each 4K byte sector with valid user data. And we no longer have to try to use all the LBAs. So as a result, the operating system and applications can purposely underutilize the logical storage space in return for performance benefits. And meanwhile, without sacrificing the true physical storage cost. So this opens very unique opportunities for system-level innovations. So to demonstrate the potential here, I will present 3 particular case studies through the remainder of this talk. So the first case study is about PostgreSQL, the second most popular open source relational database. Postgre use a parameter called the fill factor to control the amount of space reserved in each page for future update, which further determines a trade-off between the database performance and the storage cost. So if we reduce the fill factor to leave more space for future updates in each page, the database performance will accordingly improve, especially under those write-intensive workloads. But meanwhile, the storage cost will just accordingly increase. So as a result, actually the Postgre by default sets the fill factor as 100 in order to minimize the storage cost at the penalty of the performance. But interestingly, once the Postgre runs on storage drive with built-in transparent compression, the storage overhead caused by the reserved space will largely disappear because the Postgre initialized the reserved space as all 0, and transparent compression can highly compress the all 0 segments. So this naturally enables the Postgre more aggressively set the fill factor without sacrificing the physical storage cost. So to further illustrate this, so let's the blue and the black dots represent the operating points when using the hour drive and the normal NVMe drive. With the default, actually with the default fill factor of 100, both options can achieve the same performance. And meanwhile, our drive can reduce the physical storage cost by half through the built-in transparent compression. But once we want to improve the performance, that is, suppose we reduce the fill factor from 100 to 50, that means we leave half of the page empty for future updates. So under normal drive, the storage cost will almost double. And of course, the performance will also accordingly improve. But so that shows a very clear trade-off between the performance and the physical storage cost. But under the storage drive with built-in transparent compression, we can expect the same performance improvement. And meanwhile, the storage cost remains almost unchanged. So we further carried out the Sysbench TPCC benchmarking. Here we considered 2 different data sets, 740 gigabyte and 1.4 terabyte. the results here show that as we reduce the fill factor from 100 to 75, the TPS performance can improve by about 33%. On the normal NVMe drive, the physical storage space jumps from 740 gigabyte to about 900 gigabyte, or jump from 1.4 terabyte to 1.7 terabyte. But in comparison, under the storage drive with built-in transparent compression, we see the same 33% TPS performance improvement. And meanwhile, the physical storage space only slightly increased. For example, from 178 gigabyte to 189 gigabyte, or from 342 gigabyte to 365 gigabyte. So this study clearly shows that by configuring the fill factor parameter, Postgre can very nicely take much better advantage of transparent compression to further improve the TPS performance, and meanwhile, without compromising the physical storage cost. Okay, so the second case study is about how we might rethink the implementation of a write-ahead logging once we have the storage hardware, storage drive with built-in transparent compression. We know that write-ahead logging is a very critical component in all the database and the file system. So in current practice, once we write one transaction into the in-memory write-ahead log buffer and commit the transaction, the entire 4K byte block will be flashed from the buffer into one 4K byte sector on the storage. And after the transparent compression in the drive, the compressed data block will be stored in NAND flash memory. And later on, once we write another transaction into the in-memory write-ahead log buffer and commit the transaction, the 4K byte block consisting of both current transaction and the previous transaction will be flashed to the same 4K byte sector on the storage space. Then the compressed data block is further stored in the NAND flash memory. So in the same way, upon committing the third transaction, we will rewrite the same 4K byte sector again and store the compressed data block. So as transactions keep accumulating in the write-ahead log buffer, and accordingly we keep writing updated log buffer to the same 4K byte sector, the same transaction data are compressed and written to NAND flash memory multiple times. So like in this example, the same transaction 1 data are compressed and written to NAND flash memory by 3 times. So this directly leads to the write amplification. We know that a larger write amplification will inevitably cause more interference with other I/O requests, and more importantly, it will lead to a shorter NAND flash memory lifetime, particularly for the upcoming QLC flash memory. So to reduce and even eliminate the write amplification caused by the write-ahead logging, we call the sparse log data structure. The basic idea is very simple. Instead of tightly accumulating data transactions in the write-ahead log as in conventional practice, we always allocate a new 4K byte sector after each transaction commit. So, for example, when committing the first transaction, we flash the data to the storage. And inside the storage drive, the 4K byte sector is compressed and stored to the NAND flash memory, just like in current practice. However, right after committing the first transaction, we put the next transaction in a new 4K byte space and flash this into a new 4K byte sector on the logical storage space. And so then in the same way, for the third transaction, we put it in a new 4K byte space and flash it to another new 4K byte sector on the storage drive. Clearly, we waste a lot of logical storage space by not tightly accumulating data transactions in the write-ahead log. So by underutilizing the logical storage space, we eliminate the write-ahead log content write amplification. So this can help to improve the overall system storage I/O performance, and meanwhile increase the NAND flash memory lifetime. So for the purpose of illustration, this figure shows the physical write volume normalized with the current practice. Here, we assume that is right after each transaction is written to the write-ahead log, we immediately commit and flash to the storage. So the horizontal axis is the size of each transaction, ranging from 128 bytes per transaction to 2 kilobytes per transaction. The results here show that the smaller each transaction is, the more we can reduce the log write volume. For example, like with 128 bytes per transaction, the proposed sparse log data structure can reduce the write volume by over 90%. And even if each transaction is as large as 2 kilobytes, we can still reduce the write volume by 33%. All this benefit can be gained at the same time without sacrificing any true physical storage cost. Okay, so the last case study is about the hash-based key value store. In conventional practice of the implementing hash-based key value store, we have to first hash the key space onto an in-memory hash table. And then the hash table further points to the location of all the key value pairs that are tightly packed on the logical storage space, which are further transparently compressed and stored in NAND flash memory. Such an indirect addressing or mapping through the intermediate hash table can maximize the logical storage space utilization efficiency. And meanwhile, the memory footprint of a hash table is directly proportional to the number of KV pairs. So this could lead to very high memory cost for large-scale hash-based key value store. So actually, the very high memory cost is arguably is the main reason why the hash-based key value store is not widely deployed as the other key value stores built upon those more memory efficient data structures like log structure merge tree being used by RocksDB. So leveraging the storage hardware with built-in transparent compression, we propose we call the table-less hash-based key value store, as illustrated here. We directly hash the key space onto the logical storage space without going through an in-memory hash table. So by avoiding the use of a hash table, it eliminates the memory cost barrier on implementing hash-based key value store. And moreover, by relieving CPU from managing and searching the hash table, it consumes much less CPU cycles. So as discussed above, the indirect addressing through an in-memory hash table can ensure the compact placement of key value pairs on the logical storage space. But in contrast, this proposed table-less approach is subject to significant underutilization of the logical storage space. That is, almost all the pages have a large amount of empty space left unoccupied. So, but once we fill the unoccupied space with highly compressible dubbing data like all0, we can achieve almost the same physical storage cost as the current practice. So in summary, by intentionally underutilizing the logical storage space, the proposed table-less hash-based key value store completely eliminates the in-memory hash table without sacrificing the physical storage cost. So by eliminating the in-memory hash table, this key value store natively has very small memory footprint. And meanwhile, its simple data structure directly enables very high operational parallelism, short access data paths, and a very simple implementation. So compared with other key value stores, so this one is not subject to the frequent background operations like garbage collection and compaction. All these features make such a table-less hash-based key value store can achieve high performance at low memory cost and low CPU cost. So we have implemented a prototype called CalXDB around this idea and compared it with RocksDB using YCSB workload. Here is a experiment setup, and the table on the right compares the physical storage cost between our key value store, CalXDB, and the RocksDB with different compression setting. So we can see that even though our CalXDB actually consume a much larger logical storage space, but its physical storage usage is almost the same as RocksDB with very strong compression. So this figure compares the average throughput between RocksDB with the 3 different compression settings and our CalXDB. The results show that CalXDB can consistently achieve much higher operational throughput. In the case of a workload YCSBF with 50% read and 50% read modified write, CalXDB achieve 2.5 times higher throughput. And meanwhile, the higher throughput actually comes hand in hand with lower read latency, as shown in these 2 figures in terms of average read latency and the 99 percentile tail read latency. And finally, this figure compares the CPU utilization in terms of the CPU cycles per key value store operation. So the results show that CalXDB consistently consumes 2 to 3 times less CPU cycles, while at the same time achieving much higher throughput. So the advantage of CalXDB actually is mainly just comes from the fact that it completely eliminates the in-memory index data structure by leveraging the emerging storage hardware with built-in transparent compression. Okay, so in conclusion, today we talk about a new growing family of storage hardware with built-in transparent compression. In the most straightforward manner, the systems can deploy such a storage drive without changing any single line of code, and at the same time can enjoy the reduced storage cost and improve the performance. But if one would like to go one step further, such a storage hardware opens a door for very exciting system innovations. The underlying theme is very simple. Transparent compression fundamentally decouples the logical storage space usage from the physical storage space usage. This allows systems and applications to purposely waste and or underutilize the logical storage space to gain performance benefits without sacrificing the true physical storage cost. So for the purpose of demonstration, we presented 3 case studies to demonstrate the potential here. So the first case study on Postgres shows that we can simply configure a parameter to improve the Postgres performance at almost 0 physical storage cost overhead. The second case study shows that we can deploy a new sparse Red Hat log data structure to reduce the logging-induced write amplification at 0 physical storage cost overhead. And the third case study shows that we can implement a new tableless hash-based key value store that can achieve very high performance at low memory and CPU usage, at the same time without sacrificing the physical storage cost. So these 3 case studies together reveals very exciting new opportunities for system innovations enabled by such a new storage hardware with built-in transparent compression. So at ScaleFlux, we sincerely look forward to working with the whole industry and the research community to further explore how we can, how the future computing infrastructure could take full advantage of such a new storage hardware. So this ends my talk. Thank you very much.